All right, in this video, I want to talk about the formulas from chapter 8. So we're going to start with section 8.1 on arc length. And basically what we're going to do is we're going to take a function, say just a generic function from A to B. Okay, so draw your favorite function from A to B. And then we want to figure out what's the arc length of that function. What that means is that if you were to imagine that instead of this graph, you have kind of a piece of rope, and then you pick it up and you pull it tight, how long is it? Okay, we're asking what's the arc length of this curve. And what we're going to do is I'm going to show you how to use the techniques of integration that we developed in Calc 1 to do this. And we're going to split up our interval into n pieces and then let n go to infinity and we'll recover an integral. Okay, so typical story here. So here we have 0, f of x0, x1, f of x1, and so on. And if we were to zoom in on any of these pieces here, so maybe let's zoom in, say, on this interval here, so from x1 to x2. And what we're going to do is we're going to approximate it with a line. Okay, so in this case, since the function's concave down, this line's going to be under the curve. We know how to find the value of, we know how to find the length of this line using the distance formula. Okay, and so what we do is we take, in this case, it's f of x2 minus f of x1. So we're going to look at, here, let's draw a little triangle. So we have this green side, we have the purple side, and the red side. And we know that the purple side is going to be length delta x. So we know that delta x squared plus the green length, which is going to be the difference in the y values, that's f of x2 minus f of x1 squared, is going to be equal to this red length squared. And this red length, I don't know, we don't know what it is. Let's just call it, what should we call it? Let's call it, I don't know why I'm getting so worried about what we're gonna do. Just call it z. I don't know. That's gonna be z squared. And so z is gonna be the sum of the square. So it's the square root of the sum of delta x squared plus the change in y's. And what we're gonna do is we're gonna do that for each term on each subinterval, x0 to x1, x1 to x2, x2 to x3, all the way up. And so our arc length, which I'm going to call L, is going to be approximately equal to the following sum. So it's going to be approximately equal to the sum of all these values. So what we're going to do is we're going to add up delta x squared plus all the difference in the I values. So let's call it f of x sub I minus, I just want to be a little careful with the indices here, minus f of x sub I minus 1 squared. And we're going to add up all these values from 1 to n. Okay, and so just to point out what I was thinking about with the indices here, when I is equal to 1, we're going to get f1 minus f0. So it's perfect. So f1 minus f0. When I is equal to n, we get xn minus f of xn minus 1. Okay, so everything is fine. And then we have to somehow change this into a quantity that we're more familiar with. And what we're going to do is I'm going to factor out a delta x from under the sum. Okay, so we're going to factor out a delta x from under the sum. And what we're going to be left with is 1 plus, here I'm going to add this delta x to the denominator because we factored out delta x from inside, and that's already squared. And then the square root of delta x is going to be the absolute value of delta x, but it's a length, so it's positive. What we get is we're going to get that this is the sum from 1 to n of the square root of 1 plus, let's see, f of x sub I minus f of x sub I minus 1 over delta x squared. And that's going to have a delta x outside. And then what we're going to do is we're going to let n go to infinity. And so L is actually equal to this limit as n goes to infinity of this Riemann sum. and out pops an integral. And what the integral is going to be, so I'm just copying what I have for now, but what the integral is going to be is we need to think about what happens to each of these quantities. So L is going to be equal to the integral from a to b. We're going to have a square root of 1 plus something squared dx. And it turns out that this something, this should look pretty familiar to you. This is a difference quotient. And it turns out when delta x goes to 0, delta x is the distance between these two values. This is nothing more than the derivative. Okay, and so this is our arc length formula. So the arc length formula is there. Okay, and so that's the integral that we're going to have to evaluate over and over and over in section 8.1. Okay, so that's really the only formula that we really need to know for the arc length, right? So if you have a function y equals f of x, and you want to find the arc length over the interval from a to b, what you do is you compute this integral, okay, and see what we get. So just to do a silly example, let's look at the function square root of 1 minus x squared over the interval from 0 to 1. And this is going to be a quarter of a circle. Okay, so we should know pretty well what its arc length is based on the circumference of the unit circle. But anyways, we'll figure that out in a second. And what we're going to do is we're going to calculate this integral. And so to do this, we have to take the derivative. That's going to be 1/2 1 minus x squared to the negative 1/2 times negative 2x. So that simplifies to negative x over square root of 1 minus x squared. That tells us that the derivative squared, so that implies that the derivative squared is going to be, let's see, x squared over 1 minus x squared. And then the arc length is going to be the integral from 0 to 1 of the square root of 1 plus the derivative squared, which we said is x squared over 1 minus x squared dx. And so let's see, this is going to end up being the integral from 0 to 1 of the square root. We just have to combine our terms here. We're going to get 1 minus x squared plus x squared over 1 minus x squared dx. And that's going to end up being integral from 0 to 1 of 1 over the square root of 1 minus x squared. And then at this point, we're integral experts. Whether you know it or not, you're an integral expert now. We're done with chapter 7. So obviously we've done substitution in Calc 1 and then a little bit in Calc 2. We've done integration by parts, trig substitution, partial fraction decompositions, combinations of all these things, multiple integration by parts, right? So all the integrals that we need to evaluate, we have now. And this integral is nothing more than inverse sine of x evaluated from 0 to 1. And so that's going to be inverse sine of 1 minus inverse sine of 0. And so what we have to think about is what angle do we have to plug into sine to get 1? Well, that's pi over 2. And what angle do we have to plug into sine to get 0? It's 0 itself. And so this is going to be pi over 2. And what I was hinting at before that you probably already knew is that this is just kind of the piece of the unit circle in the first quadrant. We know that the circumference is going to be 2 pi r. So in our case, our r is 1. So the circumference of the unit circle is going to be 2 pi. And then we split it up into 4 equal pieces. Okay, so that's why pi over 2 is the right answer here. Okay, but everything works out. This is how the formula is going to get used. This is the only example that I'm going to do with us together in these videos. And then we'll do the rest of the examples rather than in videos, we'll do the rest of the examples in class. Okay, so that's section 8.1.